Space exploration has always embodied the pursuit of the extraordinary and unknown. From the launch of the first satellite to the exploration of distant planets, humanity's venture into space has consistently pushed the boundaries of technology, and now, one of the most revolutionary technological frontiers on the horizon is quantum computing. This vital field can reshape the landscape of space exploration, potentially unlocking new realms of possibility in space-related research and technology. However, in an unexpected twist, NASA has slammed the brakes on its ambitious quantum computer project, causing ripples in the scientific community. This decision follows a series of developments that have cast a shadow over the future of the intriguing intersection between AI and quantum computing. Coincidentally, this is something that many prominent figures in the scientific community, including Michio Kaku and Elon Musk, have been warning about for years.
Because they are so powerful, these quantum computers can crack any known digital code.
Oh.
So this means the crown jewels of any nation, with all their top secrets about the military and defense posture, all of that can be broken into by an advanced quantum computer.
I think there should be some government oversight because it affects it's a danger to the public. And so when you have things that are a danger to the public, because the intelligence would be in the data centers.
Right.
The robot's just the end effector.
Could there be unforeseen consequences or dangers lurking within the realm of quantum computing that prompted this sudden shutdown? Join us as we dig deep into the importance of quantum computing, the real reason why NASA's quantum computer project hit a pause, and the consequences behind it. Quantum computing, a field that marries the principles of quantum mechanics with the power of computing, has opened up new frontiers in science. One of the most fascinating and ambitious ideas in this realm is the possibility of simulating the entire universe using quantum computers. At the heart of this idea is the Schrödinger equation, a formula that quantum physicists have used for nearly a century to describe how particles like electrons and photons behave. Unlike the world we see around us, where things have clear positions and speeds, quantum particles exist in a haze of probability and potential. The Schrödinger equation helps us predict where these particles might be and how they might act. Now, imagine if we could use this equation not just for a single particle, but for every particle in the universe. This is where quantum computing comes in. Quantum computers operate on bits that, unlike the bits in traditional computers, can exist in multiple states at once. This property, called superposition, along with other quantum phenomena like entanglement, gives quantum computers a unique ability to handle vast amounts of information, potentially enough to simulate the complex interactions of all the particles in the universe. But why would we want to simulate the universe? For one, it could be the ultimate test of our understanding of physics. If we can create a virtual universe that behaves like our own, it would be a strong indication that our physical laws are on the right track. Moreover, such a simulation could offer insights into questions that are currently out of reach, like the nature of dark matter, the behavior of black holes, or the origins of the universe itself.
In other words, everything is going to be affected when we can multiply the power of digital computer by a factor of millions to billions. So we're talking about a new era in computation that'll change everything.
However, it's essential to remember that the idea of using quantum computing to simulate the entire universe is as audacious as it is complex. Let's break down why this is such a monumental challenge. 1. Computational feasibility, the quantum challenge. Quantum computing represents a radical shift from traditional computing. While classic computers use bits that are either 0 or 1, quantum computers use quantum bits, or qubits, which can exist in a state of 0, 1, or both simultaneously. This ability to exist in multiple states, thanks to quantum superposition, and the phenomenon of entanglement, where the state of one qubit can depend on the state of another, allows quantum computers to process a vast amount of data simultaneously. However, simulating the universe is an entirely different ballgame. The universe is made up of an unfathomable number of particles, each interacting with others through complex forces. Every electron, photon, atom, and molecule would need to be represented in the simulation. For each particle, the computer must calculate its position, momentum, and interaction with every other particle, continuously over time. But the number of calculations needed for a full-scale universe simulation is astronomical. Even with quantum computing's advanced capabilities, the current and near-future quantum computers are far from capable of handling such a task. The processing power required to simulate even a small fraction of the universe is beyond what we can currently achieve. 2. The Schrödinger equation and universe simulation, bridging quantum mechanics and reality. The Schrödinger equation is a fundamental part of quantum mechanics, providing a way to calculate the wave function of a quantum system over time. This wave function gives us probabilities of where particles might be and how they might behave. But how does this translate to simulating the universe? In theory, if we knew the wave function of every particle in the universe and all the forces acting upon them, the Schrödinger equation could, in principle, predict the future state of the universe. It's like having the ultimate crystal ball, but for particles. However, applying the Schrödinger equation to the universe raises some intriguing questions. Quantum mechanics is inherently probabilistic. It deals with probabilities rather than certainties. When we look at something as massive and complex as the universe, these probabilities become incredibly intricate. Furthermore, the Schrödinger equation operates under the assumption that quantum states evolve in a smooth, continuous way. But in the real world, we observe that particles often behave unpredictably. They can suddenly jump from one state to another, a phenomenon known as quantum leaps. These leaps pose a significant challenge for any simulation based on the Schrödinger equation, as predicting these jumps with perfect accuracy remains beyond our current understanding. In summary, while the Schrödinger equation gives us a powerful tool to understand quantum states, using it to simulate the entire universe is a task of unimaginable complexity. It's not just a matter of computational power, but also of understanding and accurately applying the principles of quantum mechanics on a universal scale. 3. Quantum mechanics interpretation, navigating the quantum landscape. The interpretation of quantum mechanics is central to the idea of simulating the universe. Quantum mechanics, at its core, is a theory that deals with probabilities and uncertainties, which is quite different from the deterministic laws of classical physics. One of the most well-known interpretations is the Copenhagen interpretation, which suggests that until a quantum system is measured, its properties are not definite, but exist in a superposition of all possible states. This interpretation implies that the act of measurement collapses the quantum state into one of the definite states. In the context of a simulated universe, this raises intriguing questions. If everything is being simulated, including observers, how does measurement occur? Does the simulated measurement collapse quantum states within the simulation? Another interpretation is the many worlds interpretation, which posits that all possible outcomes of quantum measurements are realized, each in its own separate universe. In a simulated universe, this could imply an exponentially growing number of parallel simulations, each branching out with every quantum measurement. The computational complexity of such a scenario is unfathomable. Moreover, the role of entanglement, where particles can be connected in such a way that the state of one instantly influences the state of another, even over vast distances, adds another layer of complexity. Entanglement challenges our understanding of space and time and would be a critical factor in any universe simulation. 4. The nature of reality in a simulated universe, blurring lines between virtual and real. The notion of simulating the entire universe brings us to a philosophical and scientific crossroads about the nature of reality. If a simulated universe were indistinguishable from our perceived reality, what distinguishes the real from the simulated? This idea connects to the philosophical thought experiment known as Plato's allegory of the cave, where perceptions of reality are questioned. In our context, if beings within a simulated universe perceive their world as real, who's to say it isn't real for them? This leads to the simulation argument, proposed by philosopher Nick Bostrom, which suggests that if advanced civilizations can create indistinguishable simulations of reality, it's likely we are living in one. A simulated universe also challenges our understanding of consciousness. Would entities within the simulation possess consciousness? And if so, what does that say about the nature of consciousness itself? Is it a physical phenomenon tied to the brain, or something more abstract that can arise in any sufficiently complex system, even a simulated one? Moreover, if the simulation is perfect, entities within it might never realize they are in a simulation. Their laws of physics, their history, their understanding of the universe would all be defined by the parameters of the simulation. This scenario raises profound questions about our own reality. How do we know we aren't in a simulation ourselves? In short, the idea of a simulated universe not only stretches the boundaries of quantum computing and physics, but also ventures into the realms of philosophy and consciousness, challenging our most fundamental understandings of reality and existence. In other words, this quantum leap in computing power has the potential to revolutionize various fields. NASA, in collaboration with Google, had been making significant strides in exploring the possibilities of this cutting-edge technology. To give a sense of how fast that scales, in 2019 Google reported that its 53-qubit Sycamore computer could solve in 200 seconds a mathematical problem that would take the fastest digital computer 10,000 years to finish. Last year, IBM unveiled a 433-qubit quantum computer. The 1,121-qubit follow-up is due any day, and it hopes to have a 4,000-qubit version working by 2025. So, this field is moving fast. However, recent events have thrown a wrench into their cosmic aspirations. The US government, expressing concerns over the rapid developments in quantum computing, made an unprecedented move by requesting NASA and Google to halt their quantum computer projects. This decision has left the scientific community bewildered, considering the potential benefits quantum computers could bring to space exploration, cryptography, and other technological fields. Prominent figures like Michio Kaku and Elon Musk have long warned about the dangers of unchecked developments in both AI and quantum computing. Kaku, a theoretical physicist, emphasized the dangers of AI, surpassing even that of nuclear warheads. Musk echoed this sentiment, highlighting the urgency to regulate AI development. The decision to halt NASA's quantum computer project raises questions about the interplay between AI and quantum technology. Could there be unforeseen consequences or dangers lurking within the realm of quantum computing that prompted this sudden shutdown? One major concern is the potential threat to encryption systems. Quantum computers, with their immense computational power, can break traditional encryption algorithms, raising alarms about the security of sensitive information, including financial records and classified data. So, potentially, goodbye to all military and civilian secrets, not to mention the secure transactions on which the entire global financial system depends. And with world powers competing to get first-mover advantage in the quantum computing realm, that gives the phrase quantum supremacy a geopolitical shading. Isn't that something that worries prominent figures just the teeniest little bit? Yes, Michio Kaku concedes. What branch of the government is most interested in advancements in this technology? It's the CIA. Government agencies are already beginning to issue statements saying, "Be prepared, start to make changes now in your behavior, because when this revolution is in full blast, It means that all your secrets can be read by your next-door neighbor. We're not at the point where we have to worry about this technology every day, but it's coming. Regardless, there is a significant need for the development of practical quantum computers in the coming years. Because while classical computing has made remarkable advances in the past few decades, there are still many problems that are beyond the reach of classical computers. Even a parallel computer does not offer the same exponential speedup that quantum computers provide. It offers a promising avenue for solving problems, unlocking new applications, scientific and technological advancement in fields ranging from cryptography to materials science. As Michio Kaku said, Mother Nature is quantum mechanical. The universe is in some sense a quantum computer. That means quantum computers will allow us to do chemistry without chemicals. Everything from batteries to vaccines is currently invented, effectively, by trial and error. But if you can accurately simulate chemical reactions, you don't need bubbling flasks. The secrets of everything from human aging to photosynthesis, a near 100% efficient quantum process that, Kaku reminds us in tones of wonder, takes place at room temperature, can be unlocked. Pleasingly, some of the first and most important possibilities he sets out are very material ones. The century-old Haber process for making fertilizer out of atmospheric nitrogen has made it possible to feed billions, who would not otherwise be alive today, but it consumes fully 2% of all the world's energy. Quantum computing could give us the ability to fix nitrogen without the huge temperatures and pressures required, ushering in a new green revolution. In the medical domain, quantum computers will be able to analyze how drugs work at a molecular level, model and test new ones without ever going near a patient, and analyze the vast and noisy datasets that will allow medics to spot the outbreak of a new pandemic long before humans could. Kaku envisions quantum computers sniffing out cancer years to decades before tumors form, with routine liquid biopsies performed by a smart toilet in your home. On the cosmic level, as well as predicting asteroid strikes, solar flares, gamma-ray bursts, and other planet-threatening nasties, quantum computers will allow us to model the life cycle of stars, create stable fusion reactors, and interpret the flood of data coming out of the successor to the Large Hadron Collider. Quantum computers, he says, are the tools we need to deal with problems in physics whose maths can't be handled by digital computers. Among them, the mind-bending Planck energy, 10 to the 29th power, the energy of the Big Bang, way beyond anything that we can create on the planet Earth. The mysteries of dark matter. It's very embarrassing that most of the universe is dark matter, and we don't know what it is. And even the twisting of space-time beyond the event horizons of black holes, where it's thought wormholes to parallel universes may form. In Kaku's account of it then, there doesn't seem to be a human problem that quantum computers won't be able to fix. It even may be the final step in finding the theory of everything. For those who don't know, the theory of everything is an overarching hypothetical framework that would explain the physics of the entire universe in a single equation. But unifying theories that define the large-scale cosmological structure of the universe with those that describe the minuscule quantum world of the subatomic particles has been a challenge for over a century. Figuring out such an all-encompassing theory was the dream of two legendary physicists, Albert Einstein and Stephen Hawking. But although equations that describe the universe on the largest and smallest scales have become more precise over the decades, they still don't unite to provide a complete picture of the physical world. The situation is so exasperating that some of the greatest physicists of today concede that they might not live to see it all fall into place. Hawking himself had given up on the search for a theory of everything before his death in 2018. Cambridge University astrophysicist Christopher Reynolds admits that Einstein's sense of aesthetics for the universe might be offended by the complex and messy nature of current attempts to figure out the rules of the cosmos. While the iconic German-born thinker was able to encapsulate the workings of the world on the large scale, where the rules of gravity reign supreme, in the neat E equals mc squared, things began to crumble when physicists attempted to reconcile his theory of general relativity with quantum physics, which describes the rules that govern the world on the smallest scales. According to Reynolds, standard physics right now really has two legs to it. One of them is the standard model of particle physics, which is a beautiful theory that explains the properties of matter. But it doesn't explain gravity, which is the other leg. The standard model of particle physics is the foundation of quantum mechanics that describes the world of atoms and their constituent particles, such as the quarks and gluons, that make up protons and neutrons in atomic nuclei and electrons that orbit them. The standard model explains 3 of 4 fundamental forces that govern the natural world: the electromagnetic force that holds atoms and molecules together through the interaction of their electrically charged components, the strong nuclear force which binds elementary particles called quarks into more complex protons, neutrons, and electrons, and subsequently into atoms, and the weak nuclear force responsible for radioactive decay. Michael Duff, an emeritus professor in theoretical physics at Imperial College London, said that these forces are a result of particle interactions. A photon exchanged between 2 electrons produces the electromagnetic force. The W and Z bosons explain the strong and weak nuclear forces, but try explaining gravity by interacting particles, and you get to a point where the math goes awry. Duff said, according to Einstein, it's the geometry of space and time which is responsible for the gravitational force. You can ask yourself whether gravity perhaps could be a result of a particle called the graviton. And that works quite well to a certain degree. But when you try to make a full quantum theory of gravitons, it goes horribly wrong. Your answers, which should be finite, turned out to be infinite. On the large cosmic scales, where the rules of Albert Einstein's general relativity match observations, quantum principles don't seem to apply. The same happens when one looks for the principles of gravity in the micro-world of subatomic particles. But Duff, who has spent most of his adult life trying to reconcile the two theoretical frameworks, describes their incompatibility as the disaster of the 21st century. The journey to sort out this disaster started 100 years ago, and Duff, now 74, admits that he may not see the day when the rules of chess, as he calls it, are finally cracked and the theory of everything is complete. I'm not expecting it anytime soon, Duff said. I think the key word is patience. It's going to take a long time, a lot of more research before we get there. That's my guess. Kaku's dissatisfaction with the standard model of particles, which gives us 4 forces, 12 particles, and a boson, is, he writes, at least in part because it is such a mess. A theory only a mother could love. It's like putting an aardvark, platypus, and whale together with Scotch tape and calling it nature's finest creation. The proposed successor to the standard model is Kaku's own academic specialism, string theory, which he calls crazy, but the only game in town. It's certainly beautiful. According to Kaku, the final theory is based on music. Music is based on vibrating strings. Each vibration corresponds to a particle, so the electron vibrates this way, a proton vibrates this way, and a neutron vibrates this way. They're nothing but musical notes. So physics is the harmonies that you can create on musical forms. Chemistry is the melodies that you can create out of these musical notes. The universe is a symphony of strings. And then the mind of God that Einstein wrote about for the last 30 years of his life, would be cosmic music resonating through hyperspace. Michio Kaku strongly believed that string theory is the only paradigm rich enough to explain the diversity of everything there is. The atomic theory simply says there are atoms. It doesn't explain why. String theory says it's all music, music that obeys harmonies, and these harmonies are the laws of physics. Still, the theory of everything is far from worked out. Most importantly, physicists still don't know how to pick out from billions of possible string wrapping combinations the one combination that fits our universe. Whether string theory is the right theory or not, we don't know, but it's one of the most promising candidates for the theory of everything. And according to Kaku, quantum computing may be the only way to quantitatively prove that string theory is correct. String theory exists in the multiverse. That is, we exist perhaps in parallel states which are bizarre, with new laws of physics, but we coexist with them. The way to prove it is with a quantum computer. Such a proof would shed light on a question that Einstein thought was one of the most profound that could be asked. Did God have a choice in making the universe? In the meantime, scientists keep looking for the missing piece of information that could plug the holes in a potential theory of everything. Experiments in particle accelerators such as CERN's Large Hadron Collider in Geneva, or observations of the most distant universe, may one day produce the breakthrough that generations of theoretical physicists have been waiting for. That breakthrough will most likely come from research into the nature of dark matter, the elusive invisible substance that must make up about 85% of all matter in the universe to explain the gravitational behavior of galaxies and galaxy clusters. Astrophysicists as well as particle physicists working with particle accelerators have an idea of what they are looking for, a particle called axion, which is suggested as a candidate for dark matter particles and is, in fact, predicted by string theory. Researchers think axions have an odd ability to convert into X-ray photons when traveling through powerful magnetic fields. X-ray observatories such as NASA's Chandra Space Telescope may therefore play an important role in finding out whether axions actually exist. Future missions, such as the European Space Agency's Athena mission, as well as next-generation particle colliders, may finally find the answer. What will happen when all the pieces of the puzzle finally fall into place and we understand how our world works? Will that be the end of physics? Duff disagrees. After we learn the rules of chess, he said, we can finally start playing the game. Cracking the theory of everything will surely lead to a flurry of Nobel Prizes. But what comes next? We will have to wait and see. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.